So, a bit of background history. What you see up there is something called Gustav. It was proposed in 1935 to attack the Maginot Line, but like all government projects, it fell way behind schedule, so it wasn't ready in time. And this was the attention headline-grabbing attack of about 80 odd years ago. This thing weighed 1,300 tons, could fire a 5-ton shell to around 50 kilometers, and left a crater about enormously wide. And basically, this was where all the action was. This was the cool attack of about 80 years ago. And everyone who was anyone wanted to be associated with this thing. So the downside with this was it required a 1.5 kilometer long train with 25 freight cars. Now that was just the gun and the supplies. Everything else was separate. It took, depending on which reports you believe, between 2,000 and 4,500 men to set this thing up. It required twin sets of special railway tracks, so you couldn't just run it down standard tracks. You had to build twin sets of tracks to run the thing. It had 2 entire flak battalions to defend it. And it fired around 50 shells, and again, reports vary, on about 5 different days. So one of these targets was Fort Maxim Gorky, and they fired 13 shots at it. Every one of them missed, some by hundreds of meters. So the artillery geeks had actually said in advance, this thing is not going to work, don't bother building it. But it was so cool that they just had to go ahead and do it anyway. So this was actually a considerable loss for the war effort. It drew resources away from the main attack to this stupid thing, which was just, it was a headline-grabbing attack, but that was about it. You could have achieved the same thing by just flying aircraft over it and bombing the thing. In fact, it had a squadron of spotter aircraft that could have been used to do a bombing that would have been more effective than the supergun. So surely we're not still doing the same thing today. So let's look at the threats. In the security field, we've actually got pretty good data on what the problems are. So that's the OWASP top 10, and they've been pretty much constant for the last 10 to 20 years. They've changed names a bit, and the classifications have changed a bit, and so on. But they're pretty much the same threats, meaning the things that attackers were doing 20 years ago that we didn't really know how to mitigate are still the current threats. And there's all sorts of different lists for this, for example, APIs. And again, it's pretty much constant. Some things have changed names, some have shuffled around a bit, but it's pretty much the same attacks. And they're remarkably stable over time. That's the 20-year history of some of these attacks. And again, if you really want to get geeky, that's the full breakdown of how everything's gone. And this is widespread across lots of different security measures. For example, the CRA Grand Challenges in Trustworthy Computing, this was 2003. These are the things that we need to solve within the next 5 to 10 years. Grand Challenge 1, within a decade, eradicate widespread viral spam and DDoS attacks, and similar ones. So we've got 10 years starting 2003. Retrospective in 2023, so they went back and asked the people involved in these grand challenges, have we addressed any of these grand challenges? And many participants said that not a single challenge had actually been met, meaning we've got these known problems, they're major problems, and we still haven't managed to deal with them. And again, just a random slide of example threats. So you've got, these are the top, the things with the top number of CVEs. And most of them are complete operating systems, but you look at 2 web browsers, and these are like one single application of web browser that has more CVs than an entire operating system. So we're really not doing a very good job. On the other hand, what gets all the attention in terms of attacks? If you consult the OWASP top 100,000 and you look at the appendix to the addendum to the supplement to the Apocrypha volume 127, that's the stuff that gets the news. That's what you hear, that's what you hear all the news stories about. And the thing they all have in common is that no one ever uses them, because there are about 17,000 easier attacks that everyone uses that generally don't get that much attention. So these have been called stunt cryptography. So basically you've got a 1,000% chance of recovering 2 bits of plaintext from a single message. On the other hand, the reason why attackers use the OWASP top 10 is you've got a 100% chance of recovering everything. And people really like these headline-grabbing attacks, even if they're completely practical. I'm just going to do a quick survey. Does anyone know of any cases of Roham or Poodle, anything like that, an actual attack, a legitimate attack by attackers who compromised a system using one of these stunt cryptography things? Okay, 0 hands, which is pretty much what's expected, because it's just not worth using those attacks. So my argument is, only once you fix the top 10 are you allowed to go for all the stunt cryptography stuff. So there are other cases where we've got very good measurements. For example, this is RSA key size factoring throughout the years. So the first time it was sort of done seriously for crypto was around about 1990, and it's pretty much a straight line. So you know that if you've got, let's say, a 1,000-bit key, you go across on the graph, it'll be secure till about 2040. Now, the argument is, okay, you can break 1,000-bit keys today. And yes, you can with something like that. That's a supercomputer at Los Alamos. It takes around a year's work to factor a 1,000-bit RSA key. So let's explore this a bit. Let's say you're an NSA employee and you go to your boss and you say, I've got this 1,000-bit key I'd like to factor. And the boss says, sure, tell me more. And you say, well, I need to shut down Los Alamos for an entire year just to recover this single 1,000-bit key. At which point your boss looks at you like they expect a cuckoo to pop out of your forehead on a spring. But, to make it more applicable to individuals, let's say I've got a black box, and it will, for example, the one on the film yesterday, and it will factor a 1,000-bit key in 1 year. So basically the same amount of effort. And to prove your dedication to this, you have to agree to live on a desert island, no internet connection, nothing, for 1 year while this box does its work. So you get a monthly airdrop of baked beans, which is fine. You're on the island by itself, so you can eat all the beans you want. But apart from that, you've got nothing to do except twiddle your thumbs for a year while this black box does its job. Would anyone accept this offer? Does anyone know of a 1,000-bit key that they'd want to break where they'd be willing to spend a year in isolation waiting for it to finish? Okay, again, no hands. And that's a pretty standard response. So we don't really have any rational attacks, so instead we've gone for numerology. That's a table from NIST mapping a bunch of sort of imaginary numbers to other imaginary numbers. So the thing is, where do these figures come from? The practical limits on achievable computation are around 2 to the 110 or so, and that's you're starting to use things like using the planetary core as a power source and can convert the entire Sahara Desert worth of sand into silicon and so on. So it's pretty extreme. The Bitcoin hash rate at the moment is 2 to the 94 per year, so 2 to the 110 is a reasonably safe upper bound on human computation. That means the keys for triple DES, AES 128, AES 192, and AES 256 are all basically equivalent because they're all out of reach of any imaginable human computation. They're past the 2 to the 110 event horizon. But we're using numerology, so it requires that we treat them all as distinct. So for symmetric crypto, each bit you add doubles the work factor. For asymmetric crypto, it's not that simple. You need these mappings into ridiculous key sizes. So to match each one of these basically irrelevant extra bits you add to a symmetric key, you need a vast number of extra bits added to the asymmetric keys. So for example, for AES 256, you need a 15,000-bit RSA key, even though it's no more breakable than AES 128. But wait, there's a much better one. The first quantum factorization was done in 2001, and it factored the number 15. That's not a 15-digit number. It's not even a 15-bit number. It's 3 times 5. So you could do the same with a dog trained to bark 3 times. The next record was in 2012. This time it was 3 times 7, and you can use the same dog to factor that. And then there was another attempt in 2019, which was to factor 35, and it failed. Since then, there have been no new factorization records using Shor's algorithm, which is the quantum algorithm you're supposed to use for this. There have been records announced, but I'll get into that in a minute. So basically, the scientific breakthrough in all of these cases was finding techniques to manufacture a number that you could then factor and then claim a record on it. So the standard technique is you manufacture a small number that's relatively easy to factor, and then you figure out ways of adding more digits to it that you can factor using the same method, but just you've now got many more digits on it, so you can claim a new record. They've been called Stunt factorizations. There's a paper some of you may be familiar with, Replication of Quantum Factorization Records with an 8-bit home computer, an abacus, and a dog, which shows how to use an abacus to do a quantum factorization. So even the factorizations of 15 and 21 took advantage of special tricks. So you know the factors in advance. So you basically, you know the factors, and you work backwards and build an experiment that gives you the result you want, which is the factors you already know in advance. This is not, and it's called the compiled Shor's algorithm to mask the fact that you're basically cheating. This is not a legitimate way of doing cryptanalysis because the assumption is you don't know the encryption key in advance before you even start. However, in any case, we've got 2 data points, so the factorization of those 2 values that we can put on a graph. So if you extrapolate, by 4000 AD, given the current progress, we can factor a 1,000-bit number that you can do already admittedly with Los Alamos, but with a large computer. So the thing is, it makes a highly optimistic assumption that these physics experiments scale linearly. We've got no evidence that this is the case. We've got very little empirical evidence of any of this stuff. In fact, the evidence we have, shown by the lack of progress, is that this is not the case. But in any case, possibly in 2,000 years, a physics experiment can do what a standard computer can do today. And if you guys follow the announcements of quantum supremacy, which happen every couple of weeks, even though in theory it should only be, it's a binary thing, but it keeps being re-announced. And then typically what happens is someone announces quantum supremacy, someone else comes along and says, well, actually a standard desktop PC can do that a lot better than your quantum thing. So it's kind of an established pattern. Now notice, I've been calling these things physics experiments. These are physics experiments, they're not computers. Claiming that this computer kind of misrepresents what we're really working with. So a computer takes input data, it processes it, it produces output. An experiment, on the other hand, and this is a dictionary definition I found, I can't remember which dictionary it was, a scientific procedure undertaken to make a discovery, test a hypothesis, or demonstrate a known fact. And that's what these experiments are doing. We've got this known fact that we know in advance, 3 times 5. You construct an experiment to demonstrate that 3 times 5 equals 15. So these are physics experiments, they're not computers. What this also means is that you can't pop out keys like a production line. So each experiment requires a custom designed and assembled physics experiment to get the result you want. So think sort of ENIAC from 1945, not a desktop PC. ENIAC took about 2 weeks by a 6-programmer team to set up the plug boards to wire this thing up for a particular, to calculate a particular result. So I've never found any paper that mentions how long it takes to set up the experiment to get this result. We've got 0 data points to work from. The fact that typically only a single result is produced indicates that it's a non-trivial amount of effort. And so you've got this, the earlier problem is there a key worth attacking? Well, if it takes a month to set this thing up, you better be damn sure that key is actually worth, spending a month with a physics experiment to attack. So some examples of other physics-based factorization techniques, something called Twinkle. So Adi Shamir, who's the S in RSA and a very clever guy, proposed something called Twinkle, which was later expanded to Twirl, which was essentially a physics-based factoring device. Unfortunately, he forgot to use the word quantum in it. It does actually, it uses LEDs, so there's quantum effects, but he forgot to use the word quantum in it, so nobody really paid much attention to it. So it's been suggested that it takes advantage of something called the Heisenberg-Schrödinger credulity effect. The word quantum sucks people's brains out, and otherwise sensible people suffer from impaired reasoning. Although, in honor of Metal Storm, I think it needs metal umlauts on it, so we call it the Schrödinger-Heisenberg credulity effect. So every time you see quantum computer, think physics experiment, which is actually what it is. So here's an example of this effect in action. This is a news story from a couple of months ago. So Finnish firm Bluefors, a maker of refrigerators, has signed a contract, $300 million to purchase helium-3 from the moon. It's not the script of an Iron Sky sequel. That is a serious thing. And they're going to bring this stuff back between 2028 and 2037. I assume it's a byproduct of the green cheese mines. But you just put quantum in it, and people will just give you money for anything. So how does a physics experiment break crypto? There's an example, public key cryptography. You've got this sort of vague thing saying a working quantum factorization machine goes here and profit. You can apply this to lots of things. Overpopulation on Earth, working faster than light drive goes here, profit. You want to kill Hitler, Stalin, whatever, working time machine goes here, profit. So there was a quantum physics pioneer called Wolfgang Pauli, and he would have loved this stuff. So at one point he was arguing with someone who had this very vague argument, and he drew this diagram. I don't know how legible the writing it is, but this is to show the world I can paint like Titian. Only technical details are missing. Now, if he was alive today, he would say, this is to show the world a quantum factorization machine. Only practical details are missing. So evidence for this effect. When you say working time machine goes here, as people laughed when I had the time machine slide, then it's a joke. But when you say working quantum factorization machine goes here, it's dead serious. So remember these records that I mentioned earlier. So they factored 2 carefully chosen numbers with the results known as advanced. These are known as sleight of hand numbers and stunt factorizations, which I've mentioned earlier. There's never been a single physics experiment to date that hasn't factored a sleight of hand number. For people who haven't been exposed to the 8-bit computer and barking dog paper, who here knew that there's never been a single legitimate factorization of a number with a physics experiment? Very small number of hands. Yeah, but that's, okay, so now you know. And it's a stock and trade of stage magicians. So for example, standard card trick, pick a card, any card, you have lots of smoke and mirrors to distract the audience, and then you ask, is it the 5 of spades? The equivalent for this is pick an integer greater than 14 and less than 16. Lots of smoke and mirrors to distract the audience. Is it 3 times 5? And yeah, it's only ever factored sleight of hand numbers. There's an extreme example. So D-Wave, who have some very contested claims about their supposedly quantum stuff, they advertised that they'd factored a 2,000-bit RSA number. So what they did is they chose something that differed only a small number of bits. So you take the square root, and then you guess 1 bit, and then you've factored it. Now, no RSA key ever has that form. They're specific. They have to differ by at least 100 bits. So no key will ever have that form. But if you're allowed to manufacture your own synthetic numbers that you can factor in with an abacus in this case, because you can do square roots on an abacus, then you can claim that you factored a 2,000-bit RSA number. This is the best one I've run into. So what you do is, without sort of going into the details of how these things work, but they have serious problems with errors. And so typically a lot of the work involved is in error correction, not in the maths itself. So what you do is you run the experiment and you ignore any errors. And since you know the answer in advance, you keep rerunning it until eventually, by random chance, you get the result you want. And the quote with this is, to my knowledge, no one's cheated at factoring in this way before. Given the shenanigans pulled by past factoring experiments, that's remarkable. This is from the guy who came up with this factoring technique. So basically, if you exclude the sleight of hand factorizations, our earlier graph actually simplifies to that. There is literally no data. Which coincidentally is the same number of data points we have for faster-than-light travel and Star Trek-style teleporters and time travel and so on. Now, this is a valid result because it shows that we're not actually getting anywhere. We're not making any progress. We have no empirical results. So some counter-arguments to this. We're making incremental improvements on quantum factorization. So imagine you go to your boss and you say, we've spent 20 years and burned through $100 million and we haven't got anything, but we've made incremental improvements, which means you're now qualified to be a defense contractor. Another example of these incremental improvements, so the Legio IX Hispania, better known as the Ninth Legion, they vanished in about 120 AD. And we've been making incremental improvements on figuring out what happened to them for about 2,000 years. In the same way that we've been making incremental improvements on quantum cryptanalysis for about 25 years. And we've got just as far in either case. So we've got a long way to go if we want to catch up with the Ninth Legion incremental improvements. Another thing you may have heard about is store now, decrypt later, or the SNDL bogeyman. So the idea behind this is you store 10 exabytes of encrypted data on a USB key, and then in 30 years you come along with a physics experiment and you decrypt everything. So let's look at this in a bit more detail. So it ignores the fact that you need to set up a fresh physics experiment for each new key used. So for every key exchange, you're negotiating a fresh key, which means to recover one encrypted session or encrypted message or whatever, you need to set up a new physics experiment just for that particular exchange. So the latest figures I could find were 2017. There were 7 trillion symmetric keys a year used purely for web traffic alone, not for anything else that uses encryption. And that's a limiting factor. So the German government study estimated, based on an imaginary device that doesn't exist, but they said if we had one of these, it would take about 100 days and 4 million euros in electricity to recover a single 2048-bit key. So in that 100 days, when you're running this physics experiment, another 2 trillion keys have turned up that you need to break. So we'll ignore this bit because everyone else does too. Another problem is everyone always claims these records for factorization, which is RSA encryption. The thing is, what everything uses that you're interested in for store now, decrypt later, so TLS, SSH, IPsec, WireGuard, Signal, just everything is not RSA. They don't use that. They use something called the discrete logarithm problem, or DLP, which no physics experiment has ever addressed because it's actually quite hard to cheat on this, so you can't claim a record on something where you can't manipulate the experiment. But again, so they're attacking completely the wrong thing that has nothing to do with what you actually want to be attacking, but we'll ignore that too. So the assumption is that Big Brother wants to read everything you've got. Well, what encrypted data from today will actually be useful of interest in 30 years' time? Pretty much everything that you encrypt today. Obviously, there'll be state secrets and a few other things that spooks are interested in, but most things that are encrypted today are just not of any interest. You're not going to spend 4 million euros to decrypt some online chat from last week. So here's a new research topic. Figure out some situations where SNDL is actually a threat rather than just this phantom bogeyman that we can wave around. And it's complicated by the fact we have no idea how to build these things, so we don't actually know what we're going to use to implement this threat. Another example is you're measuring it wrong. So apparently using the lack of progress in this stuff is not an accurate way to measure the lack of progress in this stuff. So one suggestion was I should be using the claimed qubit counts. But you want something where number go up. And with qubit counts, you can claim pretty much anything you want, D-wave being an example. Number go up, so I should be using that to measure progress. So yeah, that does fill the requirement. So my counter suggestion was use the number of conference papers and news stories with the word quantum in the title as your metric, because number go up, and it measures this. It's a good metric for evaluating the success of quantum. And at that point, the conversation ended. What if you're wrong? Well, wrong about what? It's basically just a bunch of facts. It's a line on an RSA graph. It's counting 0 results so far. It's the weight of Schwer, Gustav, whatever. This is just known facts. There's actually about 10 slides of references at the end if people want to look up all the details themselves. So when should we start worrying? Well, basically, whenever that turns into that, we should start worrying, and there's no sign that that will ever happen. So you've got post-physics experiment cryptography. One option, which is quite popular, is lattice-based cryptography. It was proposed about 30 years ago. It was never used because it really just wasn't that good. It was incredibly inefficient, vaguely interesting mathematically, and there were sporadic papers published, but it wasn't attacked nearly as heavily as the stuff that's actually used. Maybe we could use the time machine from the previous slide to go back in time and see if it's still okay. We're ahead in time. It's probably secure. We think it's secure. As of late 2023, 48%, so nearly half of all the NIST round 1 post-quantum candidates have been broken. Of the ones that survived that, another 25% were broken. Of the ones that survived that process and went to round 3, another 36% of those were broken. So this is really, really shaky stuff. And that's the publicly known breaks. We don't know if the NSA is sitting on half a dozen breaks that they're not going to tell anyone about. So basically, we've got very little operational experience with it. And if the operational history of every other public key crypto system is anything to go by, there's going to be lots of problems discovered. The argument is now we've got this quantum thing to worry about. Well, what if the next time the cryptographers come along and say, well, now we've got biological computing and we need to worry about that and reinvent the world yet again? So some examples of how these are supposed to be used. The governments prefer pure post-quantum. So post-quantum only, nothing else. So in effect, what they're saying is we're putting all our eggs in one basket and hoping that the dial stops spinning it, not broken. Everyone else wants hybrid, so it's a mixture of post-quantum and not post-quantum stuff, which in effect is saying we trust this stuff so little that we're requiring that you use the crypto that we claim is broken alongside it. So why are we fixated on this? I mean, at the moment, we've got a physics experiment that's no one's actually managed to assemble yet, that's faking a solution to a problem, factorization, that's totally unrelated to the one we want to solve, DLP, which falls 2 trillion keys behind for every key that it actually recovers. So this is Scribble, and Scribble can bark 5 times, which makes them more powerful and more capable than the world's most powerful factorization experiment. But nevertheless, that's been our reaction so far. So again, an analogy, let's look at subprime mortgages. So you had these things where home buyers and investors were practically given houses, so-called ninja mortgages. Mortgage brokers were earning good commissions. Fannie Mae and Freddie Mac, which is the US agencies that are designed to get people into houses, got plaudits for assisting low-income owners into housing. Retail banks made money selling mortgages to investment banks, and they converted liability to cash assets. Investment banks bought mortgages and then bundled them up into mortgage-based securities. MBS investors made money from these things, and insurance companies made money because they issued these bogus credit ratings based on these bogus bundled mortgages. The thing is, everybody was making money. So nobody, if you look at the entire food chain, from the person getting given a house all the way through to the auditors and so on at the other end of the chain, everybody was making money, so nobody had any incentive to push the emergency stop. All the data was there. I was working for a large bank in the US, or did some work for a large bank in the US at the time. And they said, look at these figures, look at these defaults and so on. There's going to be a crash at this point. And he was off by about a week. But no one had any motivation to push the emergency stop because everyone was making money. So pop quiz for security people. Which one of these would you choose? If you're an academic, would you like to publish another paper on group key management that no one will ever read? Or would you like to publish a paper on some cool new physics experiment-based thing? If you're standards groups, would you want to standardize away at some new TLS extension that nobody will ever care about? Or would you want to fly from one exotic location to another and argue over which post-physics experiment is the most cromulent? If you're a developer, do you want to audit existing code for problems? Or do you want to implement some new post-physics experiment thing that's really cool and hip and everybody's talking about it? If you're a journalist, do you want to write about this week's PHP vulnerability, or do you want to announce quantum supremacy or the quantocalypse for the 17th time in a row? And everybody chooses B because that's the fun bit. The A bit is the old grind that you don't want to get back to. And as with subprime mortgages, nobody involved has any incentive to stop the merry-go-round. If the merry-go-round stops, then everyone has to go back to doing all the boring stuff because the OBOS top 10 is still waiting and will still be waiting. So in the 1990s, there was this claim that e-commerce needs PKI to succeed. And that was the argument, we absolutely need to have PKI for e-commerce. Now, if you look at e-commerce in the 1990s, you go to a website, you enter your username, password, credit card. If you look at e-commerce today, you go to a website, enter your username, password, and credit card. So it hasn't really needed PKI. So the corrected form of that is actually PKI needs e-commerce to succeed. Without e-commerce to justify it, there's not much point in PKI. Okay, and admittedly in 2013, the NSA gave us a second reason why it's good to have PKI with TLS. But basically the e-commerce argument was the argument in reverse. Quantum computing also has the same problem. It needs cryptanalysis to succeed. If you look at almost every new quantum computing announcement, it's either just an announcement for the announcement's sake, we've done something new with bits, or it'll mention cryptanalysis because there's really not much other application for it. In other words, there's not much reason why you want to give the quantum guys a pile of money because it doesn't really solve any problems. At most, you get a few invented for quantum computers to solve until someone else comes along and says, well, actually a standard PC can do that just as well. So here's an example of a news story as reported by quantum and non-quantum media. This is the same news story. So the quantum magazine, new quantum algorithm factors numbers with a single bit. The non-quantum magazine, the quantum factoring algorithm that requires the energy output of stars, a 77-page monument to missing the point. So that's exactly the same news story, just reported differently. So again, as with the superguns, what this is doing is it's drawing resources away from the actual problem and devoting it to something that really is pretty much irrelevant. If you imagine if hundreds of millions of dollars and all the expertise that was being devoted to working on these physics experiments was actually devoted to SAST tools or scanners, just something where it's actually useful and where it's going to be addressing things that the attackers are doing. And so the thing with this is, this is a quote from a conference paper. So future adoption of these algorithms is likely inevitable, even if a quantum computer is never built, opening the door to decades of new research in cryptanalysis. So that's cryptographers are saying, this is brilliant. This is a whole career path for us. We can keep working on this stuff, even if the threat never eventuates. And so, software security designers, standards people, but again, everyone involved in the food chain thrives on this stuff. So this is something you'll never see in any security protocol or standards group discussion ever. Okay, we're done now. There's standards groups that have been explicitly shut down in the IETF, and they just continue. For example, PKIX continues under another name. PGP just keeps going and going and going and going. SSH carries on as like OpenSSH inventions that get backported into the standard. So getting back to the stock market analogy, you can make money when the market's going up or going down. You can't make money when prices are constant. So the whole stock market system is designed to have churn because churn allows people to make money. In crypto, churn means academics can write papers, implementers have something to hack away at, vendors have something new to sell to their customers. So churn's good for everybody except people primarily concerned about security and things like the OWASP top 10. Okay, this is an old saw. And churn is basically complexity serialized. Standard complexity of everything up front. If the thing is constantly changing, then you've got never-ending complexity because you can never catch up to this. So it turns the already bad enough complexity problem into a red queen complexity problem. Oops. For example, the TLS protocol alone has 60 RFCs. That's not an error, 60 RFCs for TLS versions. There's 32 further drafts in progress. So it's just under 2,000 pages of documents, which is that if you printed it out. Now, does anyone seriously think there aren't reams of vulnerabilities hidden in this complexity? And that complexity is caused by churn, that every couple of months a new RFC comes out that you're supposed to implement, that nobody has time to assess properly for vulnerabilities, and that when they get implemented, inevitably there will be bugs in there. So it is the enemy of security. The more complexity you have, okay, I'm preaching to the choir here, and the constant churn just adds more complexity and unexpected emergent properties. So some of the most secure systems I've audited were actually created by non-security geek embedded systems designers. They have bare bones TCP stack, TLS with one single cipher suite, one single key exchange mechanism, one single cipher. Certificate management is done by a memcopy because you don't really need an entire PKI in there. You just need to say, here is the certificate, does it match or not? And some of these things were designed by embedded systems guys. They had no formal education in security. They basically taught themselves a bit of crypto and that was it. And these were really, really hard to break because there was nothing there to attack. The attack surface was essentially zero. So, oh wow, finished early. So something similar to quantum cryptanalysis has already happened in theoretical physics. If you're familiar with string theory, it's non-falsifiable. It can't generate any testable predictions, therefore there's no way to say it's wrong because it's not falsifiable. And what this did is it drew significant resources away from other physics research for at least 2 decades. So for a while, if you wanted to do theoretical physics, you pretty much had to follow the string theory crowd because anything else wouldn't get funded or you couldn't find a supervisor to supervise you unless they were a renegade. Comment there from a mathematician, it's been spectacularly successful on one front, public relations. Quantum cryptanalysis is basically the string theory of security. It's never generated a single string theory has never generated a single testable prediction. Quantum cryptanalysis has never factored a single non-sleight of hand number. And for SNDL, which is the threat that everyone likes to cite, this save now, decrypt later, it's never managed anything at all. There's never been a single result for the actual threat that people like to cite as being the justification for this quantum stuff. So basically, magical thinking says it's a serious threat. Empirical data says it's bollocks. There's a great quote there from Sabine Hossenfelder, who is a physicist who did some of the stuff before getting out. You know, the reason for doing this talk is ignoring bad ideas doesn't make them go away. They still eat up funding, and killing ideas is a necessary part of science. Think of it as a community service. So what I'm trying to do here is a community service.
Do you know a prime factorization for the number 15? Good girl.
Thank you.